All right, let's go.
Number 12, Emission Nebula, the cloud that glows from the inside. An emission nebula does not reflect light from somewhere else. It generates its own light, and it does this through one of the most fundamental processes in atomic physics. Inside an emission nebula, there are massive young stars, O-type and B-type stars, the hottest and most luminous in the universe, radiating enormous quantities of ultraviolet photons. When those photons hit the surrounding hydrogen gas, they knock electrons completely off the hydrogen atoms. This is called photoionization. The gas becomes a plasma, a sea of free protons and free electrons. Then the electrons fall back. They recombine with protons. As they drop back through energy levels toward the ground state, they release photons of specific wavelengths. Hydrogen emits most of its recombination radiation at 656.3 nanometers, a deep red wavelength called hydrogen alpha. This is why emission nebulae glow red in long exposure photographs. That red is the color of hydrogen cooling from ionization. The Orion Nebula, Messier 42, is the most famous emission nebula in the sky. It sits roughly 1,344 light-years away in the Sword of Orion. It is approximately 40 light-years across. At its center sits the trapezium, a tight cluster of 4 massive young stars whose combined ultraviolet radiation powers the entire visible glow of the nebula. The Orion Nebula is not just beautiful, it is an active stellar nursery. Over 700 young stars have been identified inside it by the Hubble Space Telescope. Protoplanetary disks, called proplyds, have been directly photographed around dozens of them. New solar systems forming in real time, lit up by the radiation of nearby massive stars.
Number 11, Reflection Nebula, the cloud that borrows its light. A reflection nebula has no ionizing source of its own, no massive star nearby pumping ultraviolet radiation into it. Instead, it sits near a bright star, usually a hot white or blue-white star, and scatters the star's visible light outward like a cosmic mirror. The key physics here is Rayleigh scattering, the same process that makes Earth's sky blue. Tiny dust particles scatter shorter wavelengths of light more efficiently than longer ones. Blue light scatters, red light passes through. So reflection nebulae appear blue in photographs. The blue scattered starlight dominates the spectrum. The most recognizable reflection nebula in the sky is around the Pleiades star cluster, specifically the dust visible around the star Merope, designated IC 349. The Pleiades were once thought to be embedded in the nebula from which they formed. We now know the cluster is passing through an unrelated dust cloud. The blue glow around the stars is pure scattering, borrowed light from stars that have nothing chemically to do with the cloud itself. NGC 1977, the Running Man Nebula near Orion, is another famous example. It sits adjacent to the Orion Nebula in the sky. The Orion Nebula glows red through emission. The Running Man glows blue through reflection. 2 different processes, 2 different colors, side by side in the same region of sky. Number 10. Dark Nebula, the cloud that blocks everything. A dark nebula produces no light. It emits nothing. It reflects nothing. It is visible only because it sits between us and something bright, a star field, an emission nebula, a galaxy. And the dust inside it is dense enough to block all visible light coming from behind. The dust grains in a dark nebula are coated with frozen nitrogen and carbon monoxide. They are typically submicron in size, smaller than the wavelength of visible light, which makes them extraordinarily efficient at blocking and scattering light. Even a relatively thin dark nebula can render the background completely invisible in optical wavelengths. The Horsehead Nebula, Barnard 33, is the most iconic dark nebula in the sky. It sits approximately 1,300 to 1,500 light-years away in Orion, silhouetted against the bright emission glow of IC 434 behind it. Its shape, a horse's head rising from a pillar of dust, is produced by the erosion of a larger dark cloud by radiation from the massive star Sigma Orionis nearby. The dust pillar survives because it is denser than the surrounding material. The radiation cannot eat through it as fast as it destroys the edges. James Webb Space Telescope images released in 2024 resolved fine striations across the Horsehead's photon-dominated edge for the first time, the boundary zone where ultraviolet radiation is actively destroying the cloud's surface layer by layer. In infrared light, the Horsehead becomes transparent, the dark cloud disappears, and the young stars forming inside it become visible.
Number 9. Planetary Nebulae, the dying breath of a star like our own sun. Planetary nebulae have nothing to do with planets. William Herschel named them in 1785 because through his small telescope, the rounded, glowing disks reminded him of the appearance of Uranus. The name stuck despite being completely wrong. A planetary nebula is what happens when a star between roughly 1 and 8 solar masses reaches the end of its life. On the asymptotic giant branch, the last phase before death, the star experiences thermal pulses. Periodic explosions of helium shell fusion cause the star's outer layers to puff outward. Intense stellar winds begin stripping those outer layers into space. Over roughly 10,000 to 20,000 years, the star sheds its entire outer envelope, the hydrogen and helium that was not consumed by fusion, into the surrounding space. What remains is the hot, dense core, now a white dwarf with a temperature of 100,000 Kelvin or higher. That ultraviolet radiation from the white dwarf ionizes the ejected shell, exactly the way emission nebulae work. The expanding gas glows. The result is a planetary nebula, a glowing shell surrounding a dying stellar remnant. The Ring Nebula, Messier 57, is the textbook example. 2,600 light-years away in Lyra, a torus of glowing gas approximately 1 light-year across. At its center, the white dwarf has a surface temperature of around 120,000 Kelvin. The colors in Hubble images map different elements. Red is nitrogen, green is hydrogen, blue is oxygen. Different elements cool at different rates and sit at different distances from the white dwarf based on the velocity at which they were ejected. Planetary nebulae last only about 10,000 to 20,000 years before dispersing entirely into the interstellar medium. They are brief, they are beautiful, and they are how stars like our own sun return the elements they built over their lifetime, carbon, nitrogen, and oxygen, back to the galaxy for the next generation of stars and planets to use. Number 8. Supernova Remnant, the wreckage of a stellar explosion. A supernova remnant is the expanding debris field left behind after a massive star destroys itself in a core collapse explosion, or after a white dwarf detonates in a thermonuclear explosion. The energies involved are staggering. A core collapse supernova releases approximately 10 to the power of 44 joules, more energy than the sun will radiate in its entire 10 billion year lifetime, released in roughly 10 seconds. Most of that energy goes into neutrinos, but a small fraction deposited into the stellar envelope is enough to blast it apart at velocities of 10,000 to 30,000 kilometers per second. That expanding shell of material, moving at a significant fraction of 1% of the speed of light, plows into the surrounding interstellar medium. A shock wave forms. The shocked gas is heated to temperatures well above 1 million Kelvin. It glows in X-rays. As the remnant expands and cools over thousands of years, it progressively emits in lower energy wavelengths, eventually reaching visible light. The Crab Nebula, Messier 1, is the most studied supernova remnant in the sky. It is the debris of a star seen to explode by Chinese and Arab astronomers on July 4, 1054. A star so bright it was visible in daylight for 23 days. At its center is a pulsar, a neutron star spinning 30 times per second that continuously injects high-energy electrons and positrons into the remnant. The Crab Nebula is still expanding today, at approximately 1,500 kilometers per second. It is now roughly 11 light-years across. Its central pulsar is one of the most energetic objects in the galaxy, powering the entire nebulous glow through its spin-down radiation. Cassiopeia A, 11,000 light-years away, is the most recently formed supernova remnant with a known explosion date in the Milky Way. It exploded around 1670. Its expanding shell is now 10 light-years across and still moving at roughly 6,000 kilometers per second.
James Webb Space Telescope observations released in 2023 revealed unprecedented detail in its structure: filaments, knots, and clumps of silicon, sulfur, argon, and neon blown outward by an explosion that happened 350 years ago.
Number 7. HI region, the galaxy's star factory. An HI region is a large-scale cloud of ionized hydrogen, H2 being the notation for ionized atomic hydrogen, powered by one or more massive stars inside it. The physics is the same as an emission nebula. The difference is scale. Individual emission nebulae, like the Orion Nebula, are powered by a handful of massive stars and span tens of light years. HI regions are powered by entire clusters of massive stars and can span hundreds or thousands of light years. They are the largest star-forming structures in galaxies, the factories where entire generations of stars are assembled simultaneously. The Carina Nebula, NGC 3372, is one of the largest and most luminous HI regions in the Milky Way. It spans approximately 300 light-years and contains several of the most massive stars known in the galaxy. Eta Carina, a luminous blue variable star of somewhere between 100 and 150 solar masses, sits at its core and is considered a likely supernova candidate. The Eagle Nebula, Messier 16, contains the pillars of creation. Those pillars, 3 columns of gas and dust, photographed by Hubble in 1995 and again in stunning detail by JWST in 2022, are a feature of the HI region's physics. The radiation from the massive star cluster M16 at the center of the Eagle Nebula is actively ionizing and evaporating the gas around it. Dense clumps of material that are harder to ionize survive longer. They cast a shadow behind them, protecting material from the full force of the radiation. The result is the pillar shape. The pillars are being destroyed in real time. On a geological scale, they are already gone. A supernova shockwave that hit the region approximately 6,000 years ago likely destroyed them already. We are seeing them as they were 6,500 years ago, because that is how long their light takes to reach us. Number 6. Protoplanetary Nebula, the phase that lasts 1,000 years. Between the asymptotic giant branch in the fully developed planetary nebula, there's a transition phase so brief that only a handful are known in the entire sky. This is the protoplanetary nebula, not to be confused with the protoplanetary disk around a young star. When the AGB star has shed most of its outer envelope, but the remaining core has not yet heated to the temperature needed to ionize the surrounding gas, roughly 30,000 Kelvin, the ejected shell exists as a neutral, unionized cloud. It is not glowing. It is illuminated only by reflected light from the central star. It is cold. It is chemically complex, loaded with carbon compounds, silicates, and molecular gas. This phase lasts roughly 1,000 to a few thousand years, a blink of cosmic time, before the white dwarf reaches sufficient temperature to begin ionizing the shell and the object transforms into a proper planetary nebula. The Egg Nebula, CRL 2688, is one of the best-studied protoplanetary nebulae. It sits approximately 3,000 light-years away and shows spectacular searchlight beams of light streaming outward from the central star through gaps in the surrounding dust. The beams are not emitting, they are reflecting and scattering. The central star is not yet hot enough to ionize the gas. Within a few thousand years, the Egg Nebula will become a planetary nebula. Right now, it is caught mid-transition, a stellar death observed between stages. Number 5. Wolf-Rayet Nebula, the shell blown by the most violent stars. Wolf-Rayet stars are among the most extreme objects in the universe, typically between 20 and 100 solar masses or more, so massive and so luminous that their radiation pressure drives stellar winds at velocities of 1,000 to 3,000 kilometers per second. Mass loss rates up to 10 to the -5 solar masses per year. meaning a Wolf-Rayet star can shed the mass of an entire sun in just 100,000 years. As those winds expand outward, they sweep up the surrounding interstellar medium and the slower winds the star produced in earlier phases of its life. The swept-up material forms a shell, a Wolf-Rayet Nebula. The shell is heated and ionized by the intense ultraviolet radiation from the central star and by the shock of the fast wind slamming into slower material ahead of it. NGC 2359, Thor's helmet, is one of the most visually striking Wolf-Rayet nebulae in the sky. It sits approximately 12,000 light-years away in Canis Major. Its central star, Wolf-Rayet 7, is driving the expanding bubble that forms the helmet shape. The structure spans roughly 30 light-years. The interaction between the fast Wolf-Rayet wind and a dense surrounding cloud produces the wing-like features that give it its name. Wolf-Rayet stars are short-lived. They exhaust their fuel in millions of years, not billions. They're also the precursors to core collapse supernovae. The Wolf-Rayet Nebula around a star is effectively the pre-supernova environment, the material that the supernova shockwave will eventually plow into when the star finally explodes.
Number 4. Bipolar Nebula, the hourglass the dying star built. Bipolar nebula form when the outflow from a dying star or an active young stellar system is not spherically symmetric. Something confines the material at the equator, a dense disk of gas and dust, a binary companion, a strong magnetic field, while it flows freely outward at the poles. The result is two lobes expanding in opposite directions, an hourglass. The Butterfly Nebula, NGC 6302, is the most visually dramatic bipolar planetary nebula known. Its central star is one of the hottest known white dwarfs, surface temperature estimated at over 200,000 Kelvin. The star is buried inside a thick torus of dust that channels the outflowing gas outward only at the poles. The resulting wings span approximately 2 light-years from tip to tip. Gas in the outer edges is moving at 600 kilometers per second. Hubble images from 2009 and 2020 confirmed the nebula is still dramatically changing on human scales. Features visible in 2009 had moved measurably by 2020. Bipolar nebula are disproportionately common among planetary nebula near the galactic center, suggesting that binary star systems play a significant role in their formation. A companion star at the right orbital distance can create the equatorial disk that sculpts the bipolar shape. The central star of NGC 6302 may have consumed its companion entirely, which would explain the extreme temperature and the extraordinary collimation of the outflow. Number 3. Herbig-Haro Object, the proof that stars are being born right now. A Herbig-Haro object is the smallest and most transient type of nebula on this list. It forms when a newborn protostar, still accreting material from its surrounding disk, fires jets of partially ionized gas outward from its poles at velocities of 100 to 400 kilometers per second. Those jets slam into the surrounding interstellar medium and the cloud material the protostar is still embedded within. The collision is a shock. Gas is heated. It glows. The bright knots and bow shocks that form at the collision point are Herbig-Haro objects. They were first identified by George Herbig and Guillermo Haro independently in 1946 and 1947 in images of the nebula NGC 1999 in Orion, and now bear both their names. Over 400 are cataloged in the Milky Way. All of them lie within dark clouds. All of them are associated with young stellar objects. They are the most direct visual evidence of star formation in progress. What makes them scientifically significant beyond their beauty is what they reveal about the star formation process itself. Jets appear to play a critical role in regulating stellar mass. As material falls inward onto the growing protostar, it also fires outward in jets, bleeding away angular momentum that would otherwise prevent further accretion. The jet mechanism and the accretion mechanism are linked. The star builds itself by simultaneously throwing material away. Astronomers are still not fully certain how the jets are launched. Magnetic fields threading the accretion disk are the leading mechanism. Herbig-Haro objects are ephemeral.
They last only a few tens of thousands of years before the jets shift direction or the surrounding medium disperses. They are evidence of birth, here, now, gone on a cosmic timescale. Number 2. LBV Nebula, the eruption from the most massive stars. Luminous blue variable stars, LBVs, are the most unstable massive stars known. They sit at the upper end of the stellar mass function, between roughly 50 and 150 solar masses, and they periodically undergo violent eruptions that eject large fractions of their total mass into space. Not supernovae. The star survives. It simply explodes its outer layers repeatedly throughout its life. The ejected material expands outward and forms an LBV nebula, a shell or set of shells of gas and dust surrounding a star that is still very much alive and likely to erupt again. The homunculus nebula around Eta Carinina is the most extraordinary example in the galaxy. Eta Carinina sits approximately 7,500 light-years away in the Carina Nebula. In 1843, it underwent the Great Eruption, an outburst so extreme it briefly made it the second brightest star in the night sky, visible even in daylight despite being 7,500 light-years away. That eruption ejected somewhere between 10 and 40 solar masses of material in roughly 20 years, the most violent non-terminal stellar outburst ever observed in the Milky Way. The ejected material formed the homunculus, two bipolar lobes expanding outward at 650 kilometers per second, connected at the stellar equator by a dense disk of slower-moving material. The lobes each span roughly 8 to 9 arcseconds at their widest, corresponding to a physical size of approximately 0.5 light-years across. The whole structure is still expanding, still visible, still being studied. Eta Carinina itself is a binary system, two massive stars orbiting each other every 5.54 years, with a combined mass estimated at 130 to 180 solar masses. It is considered a leading candidate for the next hypernova in the Milky Way, an explosion so powerful it would outshine every other star in the galaxy at optical wavelengths. It has already done things no other star in recorded history has done. What it does next is unpredictable. Number 1. Nova Remnant, the shell from a star that exploded without dying. A nova is not a supernova. A nova does not destroy its star. It is a thermonuclear explosion on the surface of a white dwarf, and it is caused not by the white dwarf itself, but by material it steals from a companion star. When a white dwarf sits in a binary system with a donor star close enough to transfer material, hydrogen from the donor's outer layers flowing through the Lagrange point between the two stars onto the white dwarf's surface. That hydrogen accumulates in a thin layer on the white dwarf. Its gravity compresses it. Pressure and temperature build. When the hydrogen layer reaches approximately 10 million Kelvin, it ignites in a runaway thermonuclear explosion. The outer layer detonates. Material is ejected at velocities between 500 and 3,000 kilometers per second. The white dwarf survives. The system resumes accretion. The cycle can repeat. The ejected shell is a nova remnant. It expands outward, cools, and fades over decades. Because the ejected mass is relatively small, typically a few 10,000ths to a 1,000th of a solar mass, nova remnants are far less energetic and far shorter-lived than supernova remnants. RS Ophiuchi is one of the most studied recurrent novae. It erupted in 1958, 1985, and 2021. Each eruption ejects a shell that expands into the surrounding material from the companion star's stellar wind. In 2021, gamma-ray telescopes including Fermi and MAGIC detected very high-energy gamma-ray emission from the nova shock, the first confirmed nova of this type, showing that nova shock waves can accelerate particles to near-light speed. GK Perseus, which erupted in 1901, has a nova remnant still expanding today, now about 0.7 light-years across and still moving at several hundred kilometers per second over 120 years later.
12 types. The cloud lit from within by ionized hydrogen. The cloud borrowed starlight and scatters it blue. The cloud visible only as a dark silhouette against brighter light behind it. The dying breath of a sun-like star glowing as its white dwarf core cools over thousands of years. The wreckage of a massive star that exploded with the energy of 10 trillion nuclear bombs. The galaxy-scale factory where entire generations of stars are born simultaneously. The brief 1,000-year transition phase between giant star and planetary nebula. The shell blown by the most violent stellar winds in the universe. The hourglass carved by a dying star's equatorial disk. The tiny glowing knot where a newborn protostar's jet slams into surrounding gas at 400 kilometers per second. The double-lobed eruption nebula around a star that nearly exploded without dying. And the expanding shell from a white dwarf surface detonation, a star that blew up, survived, and may do it again. Nebulae are not just decoration. They are the record of every major event in the life cycle of stars. Birth, death, explosion, transition. Every stage leaves a cloud. Subscribe to Cosmic Hives. See you in the next one.